And the next speaker is Harvey Devereux from the Queen Mary University. And I hope you have a microphone. Oh, excellent. And he's going to tell us about improving viscosity calculations using machine learned potentials.
Right. Yes, hello everyone. Yeah, so I'm going to talk about an ongoing project we have in looking at, well, in particular viscosity, but other thermophysical properties in molten salts like lithium fluoride and others. And this is work with all of these other people. So this is what I'm going to talk about today. So first, I'm going to give a brief introduction into molten salts generally, and look at the various systems and applications of them. Then I'm going to look at viscosity in particular and how you calculate that from molecular dynamics simulations. I'm then going to move on and talk about empirical versus machine learned potentials and the ones we use in this work. And then onto our results that we actually obtain and how general they are, and then the conclusions and outlook of what we're going to work on in the future. So, yeah, the introduction. So, molten salts in brief, it's quite a diverse set of materials. So, sodium chloride is one of them, lithium fluoride that we're going to talk about today is another one. Studied for quite a long time. They have a long history of engineering applications and scientific study. Physically, they're liquid over quite a long range of temperatures. Some of them are ionic liquids, so they have lower melting points or much higher ones, for example, in sodium chloride up there. And some of their useful properties are that they can dissolve many different compounds, and they're chemically inert, so they don't react with air and water, which makes them quite useful in some engineering applications. So, yeah, this is a picture of sodium chloride salt carvings in a mine in Poland, which I thought was interesting. So, on to some of the applications, just to give a brief overview of them. So this is using molten salts for waste management, where you put solid waste into a container of the molten salt. And this catalyzes reactions and also contains some of the products that you don't want to necessarily escape into the atmosphere, solid and gases, which can then be recycled later on. So this is an alternative to, for example, directly incinerating the waste products. On to sort of energy applications, which is one of the main reasons we're interested in these, is molten salts can be used in solar cells to form part of the electrolyte of solvents, where things like viscosity become quite important in how you design them and their operating conditions. They're also a good thermal energy storage medium, which can be useful with renewable applications such as concentrating solar plants, where you can essentially store the thermal energy in the molten salt, which can then be extracted later when it's needed, which can help to combat intermittency, for example. And they're also used for cooling in Joule systems, which is what this picture is showing here in those applications. A final application I'll just mention briefly is about using them in nuclear reactors, which has long been a research topic since the 40s and 60s. And you can use them in a couple of ways. One as a coolant fluid, and another is actually suspending the radioactive, the fuel for the nuclear reactor in the fluid itself. And in these applications, the corrosive nature of these salts is a particular problem which needs to be managed. Right. So, in brief, from these applications, it's the thermophysical properties that we really need to understand. And we need to understand those for material selection as well as designing the actual systems. They have enormous implications on how these systems are designed. Studying this will help us to have a better understanding of thermophysical properties in liquids generally, and also, being able to link experimental and simulated data is still a challenge. So these are some of the problems we'd like to help address. So the main kind of workhorse we have is in what we're doing here is molecular dynamics. And in particular, we're interested in collecting viscosity as one of the key properties of these liquids. So in order to do that, you will first need to be able to calculate the microscopic stress tensor, which we can find in pretty much any MD package, I'm sure, and then compute the viscosity via Green-Kubo-like relations, which can be done for other transport properties as well. So in this case, we take the integral of various shear stress components of the microscopic stress tensor. And this kind of methodology is fraught with a number of statistical difficulties. You tend to find you need quite long simulation timeframes and/or also many repeats across different trajectories in order to get decent statistics out of it that you can then compare to experimental data and etc. Right, so the final piece behind that is then the actual model that you use to get your forces and actually compute dynamics. And two of the simplest, which have been used historically and continue to this day in these various different works I've found, are the simple Buckingham and BHM models, which are up here, which follow from parameters which are retained in the 60s for sodium chloride-like salts. Yeah, so these are two of the most basic empirical potentials we're going to look at, and we're going to use Dale Poly for the molecular dynamics of these. Another set of empirical potentials available in molten salts include the polarizable type models. So on here I put just only the polarizable ion model up here to show the story progressing from the Buckingham to BHM to including these additional dipole interactions, which are then, so for example, the dipole moments of each particle is calculated at each step during this, although we don't have an implementation of this, so I'm not going to show any results on that. Another kind of polarizable model is this SEM-Drude model, which I believe is implemented in LAMPS as well. So we would like to do the same calculations as I'm going to show today with these models, but I do not have them at the moment. Right. So onto the machine learned side of the kind of potentials we're going to look at here. So the MACE set of models, the machine learned atomic cluster expansion models, are new potentials that have come around recently and had a kind of diverse successes across a broad number of materials modeling applications, molten salts being one of them. And this is based on a graph neural network model. So you're interested in the local environment around any particular atom, and of course its own properties, which is then message passed to other neighbors to some cutoff essentially in the topology of the atomic environment. And this of course is done in such a way that the features include expected symmetries that you would expect. Yeah, and so as I've said, this works in quite a diverse range of applications across a number of different chemical elements and molecules. And for this, we're going to use STFC's Janus core package to orchestrate these simulations, make it quite simple to work with them. So that's kind of the introduction to the systems we're looking at and the methodology we're using, including the various potentials. So to move on to the kind of results that we can obtain. So this is looking at the viscosity we can obtain via the Green-Kubo method for MACE with the black squares up here, and also the BHM and Buckingham models down below, which are known to exhibit this kind of offsetting on the temperature axis, or in other words, an underprediction of the experimental data that we have, which are all in the unfilled circles. So yeah, we find that the MACE model is able to accurately predict, or actually reobtain these experimental values a lot better than the existing empirical models. Now, onto the polarizable models are also relatively good, but again, I don't have the data to show for those at this moment. So one thing we're interested in is obviously why you would have this offsetting, and this has previously been attributed in other works calculating viscosity used in lithium fluoride and other molten salts to an early melting. So if you heat your crystal, then it's known that the Buckingham BHM models will melt too early. And this has been attributed to why you have these offsetting in the results. So we wanted to look at that by looking in detail at equilibrating, melting these crystals. So there's a number of methods you can do for this. Obviously, one of the most naive method is obviously to heat the crystal, but then this doesn't give you an accurate melting point. It gives you a thermal instability, which may not coincide with the actual experimental value of the melting point. So we find, obviously, as before, that the Buckingham BHM potentials behave as you kind of expect, with this instability occurring quite a long time before the actual experimental melting points for this particular pressure, atmospheric in this case. Whereas the MACE model, kind of surprisingly, the instability occurs at the melting point, which is kind of surprising given the difficulty of accurately determining melting temperatures in MD, for example. We don't have any interfaces or any other more accurate methodologies going on here. So I'll come back to that again a bit later, but just to move on to the structure and dynamics that we see, in the machine learned potential against the empirical ones. So what I'm showing here is the velocity autocorrelation function and density of states derived from it for, in this case, just the Buckingham model and the MACE model at a little bit above the melting point in these potentials, respectively. So what we find is we find a loss of this known oscillatory behavior in the lithium VAF. And a deepening of the minima corresponding to a kind of more solid-like behavior in these potentials. And also a qualitative similarity between the two species compared to the empirical models. So onto the structure. Again, at the same temperatures, you can look at the RDFs, and we see relatively similar RDFs, but perhaps with a slightly more cohesive nature in the MACE model, which perhaps these dynamics and structure determine why the viscosity results are different. So the question then is, how general are these across other molten salts as well? So we've mainly been looking at lithium fluoride for its applications in, for example, nuclear reactors. It's something we've looked at before. But how does this work across different materials? So what we can do is, at least for the for the empirical models, we can extract the parameters from the Fermi and Tosi rules, which have been used for a long time, and simulate those in the same methodology, and do the same also in MACE, just by swapping over the configurations and the atoms, so that the potential can model those. And what we find is, generally, the instability occurs at, again, a much different temperature in the empirical models, and it's generally slightly more accurate in the MACE models. But the problem here is that we're still not, we need to look at what the melting point is in detail by actually composing, for example, two-phase systems, looking at a solid and a liquid and seeing how they evolve to get an accurate melting point, which is something we haven't done but would be nice to see. But from these results, you might think that we might want to look at, for example, potassium fluoride, which seems to do quite well, or actually in both, but in particular in the BHM, it appears to hit that instability at roughly the experimental melting temperature. So that might be a good candidate to look at the viscosity of. What we actually find is, if we then simulate this simulate this in RMD by all the same methodology, we don't actually see a good correspondence between the simulated results and the experimental results, as you might think. But this, tells us really that the story is going to be obviously a lot more complicated than has previously been attributed to just having this early onset of the melting. So, the caveats there are, we need to we want to look at more advanced methodologies to determine the melting point and see how that is different across the empirical and machine learned potentials. Obviously look at more of a phase diagram, look at different pressures, different other conditions, and also obviously the polarizable models. So with that, I'll move on to kind of the conclusions and outlook of what we're going to look at in future. So what we find is the MACE model is generally quite useful, quite accurate at predicting viscosity, at least in lithium fluoride from what we've currently looked at. And we see a kind of a similar structure but slightly different dynamics. And this, surprisingly, the MACE model hits that instability at roughly the experimental melting temperature. So our next kind of questions really are, what the melting temperature actually is in these various different potentials, see how they perform, and also to survey the other, well, like to do all 20 salts, but this is quite computationally demanding. But it would be good to see more case studies of how the machine learned potential does against the empirical models. So with that, I'd just like to acknowledge all of the people who've been involved in certainly the research, but also the code behind how we access these machine learned potentials. So yes, with that also, I want to thank the computing resources and of course the funders as well. So thank you very much for listening.
So thank you for this nice presentation. Now let's move on for questions. Any takers? Let's start with Stephen.
So the devil's in the detail, isn't it, with a lot of results, and it seems as though the detail is kind of missing from what I just inferred from there in some of the calculations. I guess the question is, what's the advantage of the use of AI, machine learning here, and at which point does an uncertainty around the ability to capture detail sort of become acceptable compared to the amount of effort needed to compute in classical?
Cost. Yeah, well, that's kind of the main problem, really, isn't it? So, giving particular numbers on how accurate you need to be, or how, I don't know. As you say, the amount of resources it's a GPU simulation, but the amount of those resources is great compared to the classical results. Having accurate viscosities and other thermal physical properties is absolutely key in designing systems that use these. So I suppose it's going to underpin whether, for example, using the polarizable models, we'll be able to achieve a more accurate viscosity, which I think we probably can. And in which case, then, it's difficult to know, really. To be honest, I'm afraid I can't give any precise numbers on when it's going to be more useful. I hope that answers it in some way, though.
Stefano?
Test go.
Hopefully we don't have to evacuate again all the room. Anyway, one of the applications that you mentioned is with a molten salt reactor. Yeah. However, a lot of these, particularly when you use it to dissolve also the fuel, the nuclear fuel, you won't have salt. You will have a soup with almost all the elements within the periodic table. How you will manage these into your machine learning potential?
Oh, as in when you have impurities and all kinds of...
You have got impurity, you start to have plutonium, you start to have, and also this stuff, you will have depletion and creation of new elements, because one of the big problems with that type of reactor is that you don't know what it is your working fluid after 6 months, 1 year, hopefully a little bit more than few years of running this.
So, Yeah, that is obviously going to be quite a challenge. I don't know specifics of actually modeling the reactors and the impurities in them.
I mean, how you would get the viscosity, how you would get the physical property on a system that is completely different from where you train your model, which is basically a pure salt.
Right. Well,
maybe let me hijack quickly. So, for example, does MACE have any information about these heavy elements like uranium and whatever, or should you start there and then maybe study these questions from Stefano?
so, well, which is, yeah, kind of what the point is. And honestly, I don't know if it actually has, if it is trained on data with these heavy elements. I don't actually know, to be honest. But obviously, that's where you'd have to start by doing that. To start with, probably. It's unlikely that it's going to necessarily generalize straight to them. So I'm afraid that probably means going back to new training data for those. But I haven't actually trained any of these the MACE model or any other machine learning models, certainly for any of these results. But it would need to be done clearly in order to facilitate these kinds of things. So if the data exists, then I imagine you probably can do that. Whether that would also be fraught with difficulties in terms of how accurate the viscosity is going to be, I don't know. I'm also not sure, are there experimental results on the viscosity in these materials that we can even look at? Yeah. So kind of flying blind there, I suppose.
That sounds like you should get together and do something.
Yeah, and as you say, also this is just a pure salt, just lithium fluoride. There are obviously more complicated salts that we can look at as well, which is probably a step between those, perhaps. So yes, definitely, we'll have to talk about that.
All right, then let's thank the speaker again.
Thank you very much.